Hello everyone. I welcome you to the day 22 of the training. Today we are going to discuss about memory designs. As we are very near to the end of the training, I want to introduce some of the project type of designs so that you will be understanding the flow of development on the FPGA. I will try to involve Xilinx ID or EDA tool again with ISC Xilinx Vivado by implementing the same project designs on it. I will also recollect your memory to the actual flow of FPGA development through Xilinx Vivado. But today we are going to discuss about memory designs, basic understanding of the memory. Some of you have asked this topic for me, um, and I want to express about memory design and what are the different types of memories that we are using and what is the basic application of memory and how can we write a test bench and Verilog HDL design file for both of them to develop a module. Now consider a module memory design for this entire session. So with that being said, let us go to the today's agenda. We are modeling the memory. Like there are very large memories as well, and today we are considering a small piece of that memory. Like in the initial days when Intel has produced ICs, there were no memory elements, but the initial designs are actually carrying one bit at a time, not bytes, one bit, and they moved on to byte and then group of bytes, kilobytes, gigabytes, between kilobytes, megabytes and gigabytes. Now the world is running under the terabyte seasons, and when when quantum computing comes into the picture, there requires a group of terabytes. There is no limit for it, and hence if we make this increase of the size of the data storage in terms of bytes, we can reach to one bigger number, which is Google. Google is nothing but having some tons of bytes in one place. That's what Google is named after. The company Google has got that name from this storage, so that's their main motto. So we are now starting at some 1024 RAM or 64 by 64 RAM designs. Sorry, I will be discussing about block RAM in the later sessions of the training as well. But today, let us understand the development of memory design and test bench analysis. So whatever design we make, this is a design. For that design, we are making test bench simulation. Every time it is mandatory, and it's a good practice to write test benches on your own rather generating it in the online session. Online tools are also available for the test bench generations. Online tools are also available for the test bench simulations. So let us go to the memory design. So introduction to the memory. Usually in the FPGA development, when we talk about static RAM or the dynamic RAM, random access memory or read-only memory like our external hard disk or the internal storage devices like HDD, hard disk drives or solid state drives. And now it is NVMe season. Like NVMe is a particular chip that is integrated as a PCIe controller chip, and on the motherboard it is embedded, or we can extend it, which is more faster than the solid state drives. And when compared to the speed of performance in the memory devices, hard drives like hard disks, which are earlier way more famous, they have a speed of some 1 gigahertz or 2 gigahertz of processing. Example, let us consider this as an example. But solid state drives, they have a speed more than the HDD. And after SSD, you have NVMe software, NVMe hardware, which is way more faster than the SSDs. And that's hardware developments from HDD to NVMe. So in the HDD, the basic memory or the data is written on a floppy disk kind of thing. We used to have a compact disk inside the HDD. If you tear it down, you can see. But in the SSD and NVMe technology, those memories, those RAMs inside them, a group of RAMs, group of SRAMs and DRAMs, those were made with integrated digital circuits. So that's an integrated IC, integrated circuits in it. So it comes with the typical chip design with the ASIC implementation, and that is a separate part of static ASIC development. But in the FPGAs, we can also make our FPGA into complete memory storage device or complete memory device which can actually read and write the information on it. So for that particular application, memory is nothing but matrix of arrays. You might have seen in the earlier sessions, like in the matrix, I have said if you have one register of array, let us consider an array, and it has some bits of data. It can be 0, 1, 0, 1, 1, 0. If this is the bits of data, and if you have 8 of them, here we have 6, and if you have 8 of them, okay, if you have 8 of them, then it is a byte. So I repeat, 1 byte of data consists of 8 bits of data. So 1 byte is equal to 8 bits. In the same way, how many number of bits are we using now? That is the major important factor for our memory design. So in terms of memory design, we usually talk about depth. So how many number of registers we have? Like in the memory, imagine it is a rack of books stored in one by one order from the bottom to top or top to bottom shelf. In that you are storing books of some information. So in that shelf, if that shelf is a memory, what are you storing in that shelf? You are storing pages of information. So each book can have, let us say, 8 pages. Like each page has an information. In the same way, we are talking about how many rows of data you have. Rows, or um, how much data are you storing in terms of number of registers. So you can stack up the registers in this way. So now we are talking about 64 by 64. Like we have 64 arrays, 64 arrays, 64 arrays, and each 64, each array consists of 64 bits. 64 bits of data. Got it? It can also have 64 bytes of data. But why am I representing how many number of arrays, how many number of bits are available in the array? That I am representing because of the matrix. And whatever you take from the top to bottom, now you have 64 arrays, like 64 registers, and each register, each array and registers, each array consists of 64 bits. Now the width, this 64 bits in one register is called as width. Such a simple understanding of the matrix. This is width and this is depth. Memory's design can be in terms of different arrangements. It can be single port, dual port, or it can be a FIFO implementation as well. FIFO is nothing but first in, first out implementation. That's another design. I'd like to introduce it in a project, as a project, but those FIFOs are nothing but memory implementation, but in terms of the output buffers or input buffer at buffer stages, like at the output of the design, like bridge between the peripherals and the internal components of the architecture. So that is FIFO. I'll explain it in the next coming sessions. But in this one register, call it as an array, you can see in an array like 63 colon 0 is the number of bits that are available here. Number of bits. Okay. Let us call this array as array. And this array is a register data type. In Verilog HDL, the data types are the key terms where you are representing the information or representing the actual element of the design. Whether it is a register, whether it is a wire, is it an input, output, or are you starting a procedural block like always block or initial begin block? Are you initializing the data, or are you starting a case statement? And also you can write functions out of it. But those things apart, we are mentioning this one single block inside the memory is having a storage of 64 bits. I'm repeating these many times because you should remember all these things as a casual way. When you do repeat a thing for twice or thrice while doing and while implementing in your projects, right, it will be very easy for you. So start doing things, start doing implementations and projects, and it will be way more helpful than theoretical learning. So here I'm trying to implement some practical or project based explanations as well. In the same way, this entire register has 64 bits of storage. Bits, not bytes. 64 bits. That is nothing but the depth of the memory is related to the number of number of arrays available or number of registers stacked upon one by one. So now memory representation can be done with what is the what is the number of registers that you have. You have 64 registers. Okay, each register has 64 bits. This is the representation of a memory matrix. You will get to know in the Verilog HDL code, but let us understand this is the architecture. What are the inputs we have? Memory read command, memory write command, memory read command, data bus to give the data into the memory, and address bus to locate where this data to be settled in which register of this data of this memory. If you have a shelf and each shelf can be named after 1 2 3 4 5 in a series, so that whenever you ask for a book and that book is stored in some shelf number called 9 or 8 or 7, and you will directly pick from that 7th row or 8th row of that shelf in a shelf. Think this as a shelf of books stored with the data. Imagine, that's a good analogy, I think, and I want to erase now everything. And you can see you have write process for a data register. Why do we need a data register here? As I said earlier in the sessions, for a memory, for a temporary process of data, for example, you can't directly access from each of the shelf. To access the shelf, you should require an external piece of elements for the memory to get the data into this and read the data from that element. So if you have an output bus like data out, you will see these representations in the coming explanations. But when you see this kind of output data coming from the memory, when you are trying to read it, you can't directly read from the memory by opening the book or by directly going into the shelf. But for the memory blocks, for this sequential element, you have a protocol. Protocol is nothing but whatever data you store, That will go to the data register first, and from that data register you can access directly. But in some memory designs, the access of the data can be done in a single click, like it directly goes without any temporary variable. So that kind of memories are different. So the basic structure, I'm explaining a bare minimum memory design which you can understand from designing in the Verilog HDL as well. So this is a basic and most used kind of structure in the memories. When you consider the memory introduction, this is the memory introduction, and this memory controller and test bench is nothing but this is an environment connected piece of hardware to the memory design in testing the functionality of it. So whether you want to write or you want to read, you can test it in the test bench. I will give an example with the test bench simulations as well with the output waveforms. So what are the instructions we have? As I said, data bus, memory write, memory write, and address locations. For the how many address locations we have, this many address locations we can see, we can actually represent. And for the read instructions, memory read and address are the commands. So memory read, this memory underscore read and memory underscore write are the actual commands, where if this is equal to 1 and this is equal to 0 at particular amount of time, you can only write onto the memory. So actually the data from the data bus goes into the memory to one of the specific location. Okay, if read is equal to 1 and memory is 0 now, then from the specific memory location with reference to the address location, from that you can take the data into the temporary register or data underscore register. It's a name that we are giving. You can also name it as temp, simple temp. And from that temporary register, your output bus is connected and you can see the data output. Okay, that is how the memory works based on the command signals, memory write or memory read. Let's go to the next topic. Here our aim is to construct a smaller memory block and simulate it. That's what I have said, like a very basic structure of the memory. Why? Because in the complex FPGA development designs in the architecture, the actual architecture is developed with the use of IPs. Most of the design elements are made up of IPs because there shouldn't be any mistake while implementing the architecture. So it should be like a piece of cake or piece of elements that are connected by our bare minimum operations, and if they are connected internally, and if we check the connections and check the simulation and verify it, and are we getting the output? Yes, we are getting the output of the desired value, then the architecture implementation is done. But here we are not designing each element of the architecture. What are we doing instead? We are considering the intellectual properties from the different vendors like Synopsys, Cadence, or any other vendor like Intel. Xilinx can have some IPs. Many other any other things which have their own IPs can get us the IPs, and we can use that IPs as a block. Actually, we have implemented this kind of development with the IPs, and from that we are actually using the larger memory blocks into our design. But now here we are making very small memory element. Usually in larger designs we are using intellectual properties. Remember this. Also, we are considering two-dimensional array of registers for the memory representation and development. Two-dimensional is nothing but width of the register and depth of the number of registers. So how many bits it has and how many registers it has. That is nothing but two-dimensional array of registers, which is nothing but memory design. That is the matrix of the memory design. So let us consider a memory block of 4 kilobytes. 4 kilobytes. 4 kilobytes. And in the digital circuits representation, kilo is nothing but 1024, not 1000. K is not for 1000, it is 1024, because the values are depending on the 2 power n. Hence, when it is near to the 1000, we call it as kilo. In the SI units, in any measurements of the distance or any other thing, K represents 1000 meters, kilometers, like 1000 meters. But here in the digital circuits, the memory for that type of number of bits, it is considered as 1024. Okay. Then the syntax of the declaring of the memory is register 7.0 and 0.1024. Why it is considered in this way? Why it is considered in this way? Because this represents for that memory. Let us consider this. If this is the memory, 7.0 should be representing number of bits 1, 2, 3, 4, 5, 6 and 7. So it is representing 7 different locations. Let us say 0, 1, 1, 0, 0 and 1, 1. 1, 0. How many does it have? I have written 8. Okay, let us not consider this thing. We have 7 locations. 8 locations actually. It consists of 8 bits, right? I'm erasing this. Okay, now 0 to 7 is nothing but 8 bits. Don't get confused like me. So it is an 8-bit storage. 8 bits is nothing but this entire thing can be 1 byte. Okay, but in terms of representing in the syntax, everything should be considered in terms of bits, not bytes. So it is 7:0, nothing but your memory location. Each location has this thing. But how many locations do we have like this? We have 1024 locations. This is 1023 actually. Bloody blunder mistake. So it's actually represented as 1023. Okay. Yeah. It's 1023 locations. So that is represented in this way. One more thing to remember is to access the memory through the address locations like mem_address. For example, you have a memory and you have this number of registers like this in the stack up. Everything will be unique. I have just given registers, but each memory location should have a memory address, right? If this is the first and foremost register, it is named after 000. That is the address location. Okay. But here, what is the address location of the last bit, last register? That is stored after the address bar can be represented by 6-bit for the basic representation, as we have considered here in the data bus. It has 6 bits of address locations like 0, 0, 1, 1, 1, 0. Yeah, in this way. So that is the address location of, for example, 63rd one. In the same way, for 1024, what is the number of bits of address? It's nothing but our 1024 is nothing but 2 power 10 is equal to 1024. And how many number of address bits we want? It is 10 bits. Now address bus should have 10 bits of 10 bits of locations, 10 bits actually representing, for example, in the last register, the last register can have an address location of 11111, all ones till the last register. Okay, represented as mem0 in the starting, or mem of 00, or mem of 010 if it is a 3-bit address, or 2-bit address, or 1-bit address, like I have said, locations of 2 3 4. So now our memory location is mem of 10 ones or 10 zeros, or 10 5 zeros and 5 ones, we don't know, but our memory location, which register are we getting the data from? Are we getting the data from the middle of the registers, or some other random register in the pile of registers? Pile of registers is nothing but, you have group of registers. Imagine these lines are each registers. Are you getting from the second one, or are you getting from the fifth one? You should have some specific serial number, right? That serial number is nothing but address, and the data in this address is located by, for example, mem of 2. How will you write for the mem of 2? You can write as 010, or you can also write it as in the 4-bit of the memory, mem 0010, if your address is 4-bit of the 4-bit address. Why am I saying 4-bit address? Representation of the address locations can be starting from 1 bit to n bits. Just address is nothing but location. For example, if it is 5, right, and I want to represent it in the 6 bits, how can you write it in the 6 bits? So 101 and 000, 6 bits. Okay, so 000 and 101, I mean 000 101, that can be the memory location for 5th register. But how many number of 6-bit registers we have? Simply 2 power 6 is equal to 64 registers we have. I mean 64 locations of address. Got it? Understood, right? So that is how memory address is also very much important. Why? Because you are designing the memory, okay, but from which location you want to write, or from which location are you want to read the memory data, or to which location are you going to write the data, you should be knowing. Sir, I mean, for the particular pointer, that is the memory address. Mem underscore address is the syntax. So mem square brackets open and representation is the syntax. So let us go to the design of the memory. You might be designing this as the first memory design for your entire training, and today let us consider 64 by 64 memory module. We have 64 registers, 64 registers, and each register has 64 bits. Okay, now and in out is nothing but so how do we design the Verilog module? First, tick timescale 1 nanosecond and 10 picoseconds. The 1 picosecond is also fine. So 1 nanosecond and 1 picosecond module mem 64 by 64 data bus we have data bus as the input, memory read, memory write commands, and address location. So we are just having a memory design with data bus, address bus, memory read and write. Just we are reading and writing commands on the, onto the memory. With that being said, in out 63 underscore 0, 63 colon 0 is the data bus. Data bus should have 64 bits of information, right? In out. So it can be bidirectional. You can read and write from the same data bus. Either you can write into the memory. Remember guys, don't get confused. Writing onto the memory or writing into the memory and reading from the memory. So there is a little bit difference. It is read from the memory. Don't get confused. And inputs are memory read command and memory write command and memory read command. So now input address locations. Address locations is 5 colon 0. Why? Because it is 6-bit input of the address. So if it is 6-bit, 2 power 6 is equal to 64 registers we have. That's the reason register, each data register, that data register is nothing but a temporary variable, temporary register used for purpose of always block, like in the procedural block I'll explain. So remember, this data register is a temporary register used for read process or write process. Register memory declaration. So you have 64 registers. This represents this, and each register has 64 bits that can be representing the width. So width and depth between mem is the name of the memory that we are looking for. And now initial begin is nothing but read memh. Read memh is a functional task, that system task, where we are using this read memh to consider this information written in this text file, input.txt file. Usually in the larger complicated designs, it is automated actually, but where you have to give the location as well, the file location in your machine where the file is actually present. So if you are using Xilinx EDA tool and you have stuck at this point, try giving the location of the file, input.txt and mem. Okay, in the mem. Now what is this mem called? The information can be considered, read can be considered into the mem register. Okay, now display whatever you have read or whatever data you have used for writing and reading, that can be displayed here in the terms of $display, $time, ns data write process done. So write process is done. That is, from this data you have utilized into the mem register. For our mem block. This entire mem block can be one big register. In the complete implementation of the FPGA architecture, one block of memory can be considered as a one register. So now initialization is done. This is initialization. This is initialization. Now come to the always block, where at every change of the value for memory write, memory read, any command, if memory write is equal to 1, that is a command. Memory read is equal to 1, that is a command. Based on our process, if you want to write to the memory write command should be 1. If you want to read from the memory read should be 1, as I have said in the previous example. Now you need any address location changing. For example, in the previous state, you have read some information from the address location of 5. Now for the next iteration, you want to read from address location 10. Okay, go to the 10th location. So address is also changing. For this change value, always block is active. So whenever you mention in this way, right, for every change of the value of these inputs, your entire block is processed. So this is procedural block again. If you want to begin, end. So I want to erase all these things. Few of them you can keep and erase all link. So now let's consider for all these value changes, your always block is active. Begin the process with an end on it. And if first condition, if memory underscore read command is value 1, then memory underscore read value is 0. And means logical and means, and the both conditions you have written should be true. They should be in that state. If they are this, memory underscore write command is 1, memory underscore read command is 0, you have to begin and memory address location. So what are you doing here? Memory write is 1. So this process is write process. And how this write process is happening? To the specific memory address location, to the specific address location, any address location. For example, this is the address location 5. For this address location, you are making it active, and whatever the data comes from the data bus, right? Data bus is in out. It is in out data bus. Okay. In that data bus, whatever data comes, like in the 64-bit data bus, that will go to this address location. How it is going? By this command. By this statement. And data register is equal to open. You always have a data register in the memory design. So this is data register. Okay. So that is data register, and end it. Else if memory read is 1 now, initially memory read is 0 and memory read is 1 and this is false, what happens? Display time, whatever the memory address location consists, now the data for this data location, for example, if this is the data register, memory address considered now, let us say some data address location of B, this is sent to the data register. So this is sent to the data register. Okay, now data register is there, and that data register value is considered in the display. Printf. So now you have data register. You should printf. You should display what is there in the data reg. To display the data there in the data reg, you can see, you can consider data register and also address register and $display $time. Keep an understanding, keep focus now. Whatever the data register you have written here, that is considered in this location, and what is the address is there, that is considered by this header file, %h hexadecimal. Okay, %h is nothing but hexadecimal. All these values can be in the hexadecimal. You understood this representation, this syntax, right? And display $time. Next is data bus data is. What is there in the data bus now? That can be considered by this data underscore bus at this point. Understood? End the block. See, if you have got confused with begin and end, when to write and when to write the end, simply if you know that more than two statements are there with you, then simply write begin and end within the else if condition or if condition. There ends the matter. In the if condition, here you can see begin and end because of two statements. In the same way, in the else if condition, you can see it more than one statement. Hence, you are writing begin and end. Don't make the syntax error. When you write begin, write end, and in between both of them, write the statements. There will be no syntax error after that. Okay, this condition is also good. Else, we should have a default value called data register. Data register is 64 bit hexadecimal open, and hence whatever the data register is there, that data register value can be shown in the data bus. So why are we assigning? There is a question here. Why are we not using directly here in the write process, right? Whatever data is there. Okay, I'm explaining with red mark. Now, why do we have this assign data bus and data register in the end? Why? Because in the write process, whatever data you have in the data bus, consider this is data bus. This write process is direct into the register. This is direct, single action. It goes into the register, some register. But for getting out, it should go to the temporary register. Why? Because, listen carefully, this in-out operator kind of variable or the input in-out registers, I mean in-out wires, both bidirectional wires cannot be considered inside the always procedural blocks. This is procedural block. If we try to consider it, there will be a conflict of the operations. So to avoid that conflict of operation, we don't consider, we don't consider the in-out operations, in-out type of data bus or any other variable. The type of wires or the functionality, we can't use it in the read process, in the procedural block. So the data comes into the write from data bus to the memory address, but here in the read, so this is read, so this is write. Please make a note of these things. Don't get confused by seeing the Verilog HTML code. Each line by line explanation is given here. That's what I am repeating these many times. If it takes time, let us take time to understand these scenarios. So this is write and read. Okay, in the read process, memory is going to the data register. Some in usual cases you can see temp. Name can be temp typically, but I have said a data register because that can be a temporary data register. Okay, so now in the read process, you are reading from the memory into the output. Okay, so or you are again reading into the data bus. This is the process. So let me draw a diagram, and you have a stack of registers here, and in the temporary register, for example, let us name it as temporary, and you have a bidirectional data bus. Understand how the read process is happening. Read process is happening from the address location, from this memory location. All the information all the information is sent to temporary register like this data register, and from that data register, what are you doing? You are making into the database. So you are getting into the database. So this is in and out. So this is a bidirectional bus interface, but in the later designs I'll try to implement how can we change this bidirectional to single directional, and how can we use the same data out and data in inside the memory registers. So that is what this entire design looks like. Now let us go to the next block. So part 2 of the memory design is nothing but test bench. So this test bench has quite a lot of explanation. I want to split it into the blocks, but let us consider um, first part of the test bench. First part of the test bench is input, module mem underscore tb. Quite a good representation of the test bench module. Now this is a design. Test bench is a design. Like design. This is the design. So that test bench design. For that we have to give a name. First step is done. Second step is representation of registers and wires. In the test bench I am repeating what are the inputs in the design stage. That inputs are wires in the design stage, and in the test bench phase those wires can be registers. If input is A, and you can mention wire A, but now in the test bench it should be register A. Got my point? All inputs will be turned into register, and in the same way all outputs you have mentioned it as register, and that register can be considered as wires in the test bench. So vice versa. Why? Because outputs of a design is considered into the test bench input. Understand the logic here, don't get too much confused. And from the output, from these outputs of the test bench are connected to the design as a input. Hence all inputs are registers. So at output you can see register, all inputs are wires, and wires, all inputs are wires. Okay, so this is the declaration. Now whatever you have written in the in out like register and register, those can be wires. Okay, memory is again a register, you should mention it as a register again. Now instantiation of the unit understand test. So this design should be considered into the test bench. So how it is considered? By instantiation. So mem underscore mem 64 by 64 UUT, and data underscore bus, memory underscore read, and memory write, and memory read, and address. This reference of the representation can be made as it is how you have made in the design phase. So you can't alter the positions of input and outputs. So you should be representing the same, and you should give a label of the design. Now come to the next memory design, that is initialization. For that initialization, initially memory write command and memory read command are 0. So it is 1 bit 0. It is 1 bit 0. And address is 0. It is at initial point every time the initializing inputs, and after 20 nanoseconds you can see memory read and memory write are interchanging. So now reading is happening for 1 and memory write is 0 at this point. So we are not writing into the memory, we are reading from the memory. What is the memory? So for that address location we have given 6 bit hexadecimal 7. So it will be 777 777, that can be address location. So in this similar way, you can represent after 10 nanoseconds, if for the address location of this thing, after 10 nanoseconds, display the memory read from the address. So whatever the address you have, that can be read. And condition is address location should be printed, and data bus should also be printing the value of what data bus is having. Why? Because this data bus is assigned from the data register. Simply you can also mention, if you have mentioned data bus as the wire, right? From that wire you can mention data bus here. Okay. Similarly, you can test for another 5-6 values with different locations of the address. You can read, and it is considered from the input.txt file, read mem. So this is written into the memory, right? In the design, we have written into the memory, but in the test bench, whatever the data written in the memory, that can be read, that can be taken from the memory. So, and in the last part, you can write these for the waveform generations. So let us go to the EDA playground, and in this EDA playground you can write the scripts in the design file. Whatever Verilog HDL code I have explained, you can mention it in the Verilog HDL. Try on yourself and also write the test bench for it. So this is the test bench. In this way you can write. So this is all I have explained here. So after making the design and test bench, save it first, and by saving, you can see the EDA playground with left side tools, and you can see the tools and simulator. Select Aldec Rivera Pro. This is one of the leading vendors for the simulators, and this is an online simulator that we can use. And Synopsys is another company for simulations, and we are using Aldec now. Let us take Aldec, and libraries will be internally linked. We are not mentioning any libraries as we do in the VHDL. And time scale we have given as 1 nanosecond, that is considered from the time scale we have written. Okay, now go to the output. What you have to see, open EP waveform after run and show output file after run. So this is mem64. Until you give this, you can't run. So run it and try to run this. I hope I will be showing the waveform. See, okay. Before going into this thing, let us see how this memory is jogging now. Memory is read. Also memory is read. We are actually mentioning $readmemh input.txt into the memory file, right? That input.txt file is this text file we have given. So this text file you can add as one of the primary sources or add sources in the EDA tool. In the Xilinx Vivado, while we are developing some of the thing, we are adding constraint file, we are adding simulation file, we are adding the design file. In the same way, we can also add this .txt file in the add sources. For that, we can also give any information. For example, if we give if we can give another value instead of 777, let us say 755656 and 5557. So if it is the thing, you need to save it again, and from that save, if you can run it, let us see what kind of waveform is generated from this value. See, you can see whatever the value, this is in hexadecimal radix, and you can also turn it into binary. For every 2 bits, you can mention what is the value you are getting, and see, initially it is at default. By default, data bus is open, and that data bus is getting the data from data registers, because here in the data register in the design file we have given default value as high, high impedance, like Z is nothing but high impedance, that is open. So that is represented here in the open. Then after uh, in the output, if you can see, in the 0 nanoseconds data process is done, data write process is done. So this data write is done. Here you can write, read and write. So write process is done. So after 70 nanoseconds, like here after 50 nanoseconds address is 0. After 20 nanoseconds memory read is 1 and memory write is 0. Hence read is 7. And why are we taking the address location 7? Randomly we have took the address location of 7. So for this address location of 7, see, consider these serial numbers here. This 7th location, like if it is 0 0, if it is 0th address location, 0 1 2 3 4 5 6 7, 7th location is this address location. So this is the address location, 6-bit hexadecimal 7. So if it is the data memory, if this is the memory block here, in this memory block I am reading the memory from the 7th location. So from that 7th location you can see what is the 7th location data I have. Data read from the 7th location is C. This is the data, and that data location after 70th nanosecond, so it is C. 69,955. I can move it to 70 nanoseconds. Okay, after 70 nanoseconds, I can't make it to the closer. Okay, nearby 70th nanosecond. After 70th nanosecond, what is the data? It is 756567. I can zoom in, zoom out. See, you can see the data. And after how many nanoseconds? From here it is 70th nanosecond, right? In the second data, you can see here you have 70 nanoseconds. Let us add after 10 nanoseconds you are displayed. So 80 nanosecond, 100th nanosecond. 100th nanosecond address location is 061. I mean that is the output, I think. So yeah, 100th nanosecond. Data read is 6, all 6, because address location I have given is 606. So consider this is 0th location, first location, second location, third location, fourth, fifth and sixth. Forget about this 7, but this serial number you can name it as this is 666. And what happened to us? That data is printed here. Similarly, for every 30 nanoseconds, for every 30 nanoseconds of the data, you can see a new data is printed. Likewise, if you want to see same another location, right, I can do this thing. So now our address location, name it as another 5. I don't think I have used 5. Okay, 5. Now fifth location, let us see what is the data printed after the 9th address location. So I have saved it and let me run. Let me run quickly and see. You can see the 5th location is the data. Okay, I can't drag it in a bit, but you can see the 5th location, right? This is the data printed, and at you need to add after every 30 nanoseconds. Here it is 70, 100, 130, 160, 190 and 220. It is 250. Now 250 plus this data, so 250 at the nanosecond. You can see at 280 nanosecond, after 10 nanoseconds after this data, you can see the value is written as, and data bus is this. Okay, so this is how memory location works, and input is taken from this thing, and you can see the simulation as well. After every EDA simulation, just check the conditions here in the terminal window. You can see the output as it is, and this is a basic example of D flip-flop. In the same way we can take it for the D flip-flop. Mention the modules and module D flip-flop and inputs, clock reset and D, output Q and Q bar. You can see the input and outputs. Register Q, assign QB is nothing but negation of Q, not Q, that is an operator. Negation of Q, always at the rate of posage or the posage of the reset, begin the process. If reset, begin, Q can be 1 bit 1, and else, if else, if not reset, Q will follow the value of D. Okay, initially the value of Q can be 1, or else the data can be transferred to the Q output. So that is the basic representation of D flip-flop. Let us go to the test bench. This is how you can write a test bench in a series order, like mention the time scale, module D flip-flop underscore TB, good representation. Registers and wires, as you can see, input and outputs can be reversed. Inputs are wires here, and there it is register, and registers and wires are represented, and you have to instantiate the thing with the design under test. So why are we getting this DFF and DUT? Because this test bench module will be taking the consideration of the design file of the module. So whatever module you have written, take this DFF, write it here, label it with DUT or UUT, or label one with a label, and have these input outputs in the way you have mentioned: clock reset D, Q and Q bar, and clock reset D, Q and Q bar. After that, initialize the block, initial begin. You are here initializing the output waveforms, and initially clock is 0, reset is 0, everything is 0 at first starting point, and after 1 nanosecond reset changes from reset is equal to 1. Why reset is equal to 1? Because we are checking if block. Here reset is equal to 1. Let us take here reset is equal to 1, and that is verified in the initial. After reset is equal to 1, D is equal to 1 bit binary 1. Let us assign a value and display release reset. D is equal to 0 and reset is equal to 0 after that. Then display after 20 nanoseconds. What you can see, whatever the reset value is there, that can be seen here. And after 20 nanoseconds, display toggle clock. The clock is displayed at after clock is equal to 1. That clock is taken into here, and clock is represented here. Display and task display. You can write #1 after $display is nothing but printf statement in the C programming. So D, what is the value of D? %0h. What is the value of Q? %0h. Q bar is also %0h. So why do we represent it with %QH? These are the values of representation for the input and outputs. So for the percentage decimal, right, usually we represent it with %D, and in the C programming %D is integer value. In the same way, we are considering this D is represented with this, and Q is represented with this, and this QB is getting the information from this end task and end module. So that is how you can write a test bench for D flip-flop. It is better to understand this D flip-flop design. It is good because you will mostly rely on the D flip-flop in the entire FPGA architecture. So that is today's class. I hope you have learned whatever you want to understand between memory design. Just a recap of everything. Go through it once or twice this training, and if you have any questions, just let me know. I'm here to help you. Thank you.